All right. Okay. So now, organic chemistry. Okay. So, ladies and gentlemen, can I ask you, if you hear this term, organic chemistry, what does it make you? What do you think organic chemistry is? Don't shut up. Yeah.
It's like fuel. It's like the different types of fuel.
Okay, so you think of fossil fuels?
Not necessarily. It's like fuel made up of like carbon and hydrogen.
Fossil fuels, hydrocarbons.
Yeah.
Fossil fuels. So you think of fossil fuels. Okay. Okay. Chemistry revolving around carbon or based on carbon. Very good. Anyone else? Josh.
I think about the structure of life.
The structure of life. Very good. So you have heard of organic, Josh?
Like the processes, like for example, we breathe in oxygen, breathe out carbon dioxide, those sort of processes.
Okay, so it's to do with life, eh? It's to do with life. So organic chemistry in its inception was the chemistry of life, right? Until certain chemists were able to synthesize certain organic compounds that were thought to only be possible to be produced by living systems, okay? So, for instance, something like urea, which is found as a product of the urinary system of living organisms, was actually synthesized. And then it was realized that you can actually produce organic compounds without there being a living system that's doing it. All right. Organic compounds, the amount of organic compounds that we know of runs into the millions. It's well over 13 million different organic compounds. And at one stage, they were adding over 100,000 organic compounds per year to this massive reservoir of organic compounds that we knew, as opposed to, I think it's about 300,000 inorganic compounds. So an inorganic compound is something like, for instance, nitrogen dioxide. It's got no carbon in it. NO2, okay, is not organic, right? Something like SO2, for instance. Water, H2O, would be deemed to be an inorganic compound, okay? So, organic chemistry is the chemistry, we're not going to call it the chemistry of life, because most of organic chemistry today is not from living organisms, okay? It's synthesized. So for instance, plastics like this plastic is a polymer. This polymer is based on organic chemistry. So polymerization is processes of producing polymers, plastics, and it's not through life systems. Okay, yes, you do get polymers in living systems, but you can produce polymers without an organism. Okay, so we're going to refer to it not as the chemistry of life, but the chemistry of carbon-based compounds. Right. Now, I have not a challenge, I have a question for you. That's not even a problem. I would like you to please draw the Lewis diagram and the Aufbau diagram for a carbon atom. You have got periodic tables. I would like you to draw the Lewis diagram and the Aufbau diagram for a carbon atom. I think it's time for allergies again. All right, so draw the Lewis diagram and Aufbau diagram of a carbon atom. The carbon we are looking at is the most general isotope, carbon 12. All right, but that doesn't really matter because we're looking at the electrons. So we want the Lewis diagram of a carbon atom. In a Lewis diagram, we only show the valence electrons. Okay. Which group does carbon sit in? 4. So how many valence electrons will carbon have? 4. Okay. So remember what I taught you about s orbitals. If we look at the Aufbau diagram, right? If we look at the Aufbau diagram, let's do it in a different color. Okay, if we look at the Aufbau diagram, there is the axis for energy. Right, we have the 1s orbital, and we put 2 electrons in there. Then we have the 2s orbital, and we put 2 electrons in there. Now remember that energy level 1 is the core energy level. So energy level 2 is going to be the valence shell or the valence energy level for a carbon atom. So it's going to be 2s, 2. So I'm going to put 2 electrons into the s orbital in the valence shell. So those 2 electrons go together. Okay. Then we still need to account for 2 more electrons. So we go to the 2p. We look at the 2p. Now remember the 2p, there are 3 orbitals. They're all the same energy. And we are now going to put the remaining 2 electrons in 2 separate p orbitals. Why?
Because of
Drink?
Follow the blocks before you can.
Yeah. Hund's rule or Hund's rule, we first put an electron in each of the p orbitals. Why? Because that minimizes the repulsion, which results in a lower energy system. So we first put 1 electron into each p orbital before we start filling p orbitals. So if we look at that, then we put each one of those 2 electrons in separate orbitals. So if we think of the Lewis diagram in terms of orbitals, right, there are 4 orbitals around that carbon. One of the orbitals is going to be the s orbital, it doesn't matter where you start, and then the other 3 will be p orbitals with only 2 electrons in each. So, okay, so there's the Aufbau diagram, and here is the Lewis diagram. Okay, I have another question for you. What is the valency of carbon? 4. The valency of carbon is 4. All right, so what I want you to do now, I want you to draw the Lewis diagram of CH4, which is methane. Okay, so draw the Lewis diagram, LD Lewis diagram. Draw the Lewis diagram of methane. Methane, which is CH4. Remember earlier in the year, we did chemical bonding. And when we did chemical bonding in grade 10, we drew certain molecules. One of them was methane. Okay, methane is produced by organisms after the food has been processed. Okay, so methane also, for coal mining, methane deposits used to be found. We used to find these pockets of methane. And they were very dangerous for coal miners because if the guys were using those, nowadays they use electric lamps, but they were using lamps with flame, they used to have these massive explosions. Does anyone know what the detection system was that they used?
Wasn't this canaries?
They used canaries. Yeah. So when the canary stopped singing their song, you know that the canary had gone, the canary had died from the methane. Yeah. Nowadays we use electronic detection systems, but they used to use canaries. Okay. So methane is the most basic organic compound. It's the most basic hydrocarbon. So I would like you to draw the Lewis diagram of methane. Okay. Yes.
What do you mean by the most basic?
You'll see soon enough. It's the most simplest of all organic compounds. It is the starting point of organic chemistry.
So it doesn't, so I have a tutor that is.
Sorry guys, sorry, one person at a time.
So like I have like this tutor who goes into chemical engineering, and so she taught me a bit of organic chemistry.
She probably knows more than what I do. Yeah. Okay.
So doesn't it rank from methane then?
Hey, yes, but you're jumping ahead. I don't want to jump ahead. Yes, you're absolutely right. We are going to be doing that by the end of the lesson. Okay. Absolutely. Meth is the simplest. Okay. So draw the Lewis diagram of methane. Have we done that? All right. So we start off with carbon. 1, 2, 3, 4. Hydrogen. 1, 2, 3, 4. Okay. Does this ring a bell? I have a problem. If I take the Lewis diagram apart and I take the hydrogens away, so if I now look at what the Lewis diagram of carbon looks like, that diagram is definitely not the same as that one. So what has happened? Declan.
Carbon hybridization.
SP 3 hybridization. Yeah. So what has happened is the following. If I now go and I take a look at this Aufbau diagram, this is for an unbonded carbon atom. So at the beginning of the year, when we asked you to draw the Aufbau diagram of a carbon atom or a nitrogen atom, we were asking you to draw an individual atom in an unbonded state. In other words, not bonded to something else. All right. So if I now take this, and I now go and I'm going to just copy this quickly, right? And I now go to here, okay, and I look here. So in an unbonded carbon atom, it looks like that. Now, when carbon goes into a bonding situation, the laws of chemistry do something very strange. They mix orbitals. So there's a process that takes place called orbital hybridization. And if my memory serves me correctly, this won a Nobel Prize. Okay? So orbital hybridization says that these valence orbitals here, they mix, right? And in mixing, what happens is, if I look at the energies now, right, so the 1s orbital, the energy doesn't change on the same energy, okay? But what happens now, the 2s and the 3 2p's mix. Now, I've always had a question about this. How does nature know that something should exist if it doesn't exist? Okay? An orbital is a region of space in which an electron is most likely to be found. Does this orbital exist? It doesn't exist until there's an electron in there, not so. So how do these electrons know that that orbital exists? They don't, okay? So there must be something driving it, and what drives it is energy, okay? I'm not a quantum physicist, I'm certainly not a quantum chemist, but my limited knowledge of chemistry, I know a little bit about quantum mechanics, being a physicist, is that quantum mechanics is driven by energy, all right? So these 4 orbitals mix, and so what they form is they form a new type of orbital that sits, the energy sits between, not exactly between, but between where the 2s and the 2p are. So these four orbitals, 1, 2, 3, 4, are now all the same energy. All right? And so they are now called 2. We took an S, we took 3 P's, and we don't write the 3 down in the subscript, we write it up there. So this is not a power, eh? They're called 2 sp3 orbitals. 2 sp3 orbitals. Now, the sp3s, very interesting, they have got a very specific arrangement in space, okay, which I'm going to show you what it results in. All right, but now I've got 4 electrons there. What rule do I use for filling up those orbitals? Hund's rule. 1, 2, 3, 4. What has happened to that lone pair that originally existed? It's gone. How many spaces are there available for electrons from other atoms to come into this atom's valence shell? How many electrons will be involved in bonding? Got a valency of 4. So therefore, now your carbon is going to look like this. It's going to have 4 sp3s. So this won't be an s and 3p orbitals, this will be 4 sp3s, and in each of them you are going to have 1 electron. But that looks like the Lewis diagram for a carbon that's in a bonded situation. So when carbons bond, they form an outer valence orbital structure that is different to when they're on their own. All right, so therefore now we can say this has got a valency of 4. But this is when carbon is in a situation where it is part of a molecule. So this is for a bonded carbon atom. Okay. Now, this is known as a methane structure, and in organic chemistry we have a very, very clear specific naming system called IUPAC. IUPAC, okay? We're going to learn about IUPAC. The IUPAC naming, IUPAC stands for International Union of Physical and Applied Chemists, IUPAC, okay? So meth implies only 1 carbon. Eth, 2 carbons. Meth, F, prop, but, pent, hex, hep, op, non. We're going to learn about that, okay? So, yes, fine, okay. So now, ladies and gentlemen, what I want to show you is I want to show you a ball and stick model of a methane molecule. A ball and stick model. Now, these models have been designed so that they represent the structure, the orbital, the outer valence shell's orbital structure. Now, if you look at this, I'm going to pass it around. I'm actually going to take a photo of it. All right, I'm going to take a photo, and then I'm going to pass it around. Okay. All right. That is each of these bonds. Each of these bonds here is an sp3 bond where the hydrogen is sharing an electron with each of these orbitals. Okay. Now, so I'm going to pass it around, and it is really important that you get a feel for the shape, because this shape is exceptionally important. It's called a tetrahedral shape. All right, a tetrahedral shape. Does anyone want to venture why we would call this tetrahedral? What does tetra mean? Tetra means 4, eh? Okay, okay, please. The man is right. Thank you, Josh. It's called tetrahedral because if you now go and you take a look at it in a certain way. Sorry, I took a photo, my bad. Okay, let me just quickly go back here. All right, if you look here, if you draw an imaginary surface that joins the 3 nuclei on that side, and then the 3 nuclei on that side, and the 3 nuclei on the opposite side, and then the 3 nuclei at the bottom, you get 4 surfaces. Tetrahedral. Now, that tetrahedral structure becomes very important because it's a symmetrical structure. It means that all these angles are exactly the same. And so from an energetics perspective, what you're getting here is one of the ways of looking at why sp3 orbitals form is because in a setup like this is which minimizes these sp3s, the positioning of them minimize the repulsion. And by minimizing the repulsion, they make the molecule more stable. Okay. Now, ladies and gentlemen, we have got, I just want to see how many more minutes we have left because it's just a single lesson. All right, it goes until 12:15. Yes.
Sorry, sir. I just wanted to ask, in a test, if you were to ask us
Someone's asking a question.
to draw the Lewis dot structure of just a singular carbon atom, would we have to draw the unbonded form?
It depends. If we ask you to draw the Lewis diagram of a carbon atom, then it's unbonded. If we ask you to draw the molecule of methane, then it's going to be bonded. Okay. Now, so if we look at methane, all right, methane, the Lewis diagram of methane is that. If we looked at the Cooper notation, and this is also very important, can I ask you to please draw the Cooper notation of the methane? The Cooper notation.
Sorry, sir. Does this occur with other orbitals, like d orbitals?
You also get sp2 hybridization.
What is this 3p in sp3? Oh, I see.
So what eventually happens is
Something physics doesn't
this orbital model is limited. So when you start going into d orbitals and more bigger atoms, it's better to move to something called molecular orbital theory. All right, now, ladies and gentlemen, do you agree with me that the not the Lewis diagram, the Cooper diagram would be this?
Yeah.
Right, we have another name for this when we do organic chemistry. Thank you, Josh. And the name for the Cooper notation is we call the structural formula. Right, that's called the structural formula. Would anyone like to venture another way of representing this in a more concise way?
So sorry, not answering the question, but can you just remind me again why sometimes you use 2 lines instead of 1?
2 lines will be when there's 2 bonds between 2 carbon atoms, when it's a double bond. Yeah, so each of these are single bonds. So very, very good question. Very good question. So if you look at this particular, just want to see here. Right, if you take carbon dioxide, for instance, all right, just going to show the carbon dioxide. Then can you see that there are 2 bonds between the carbon and the oxygen? Can you see the carbon's got 1, 2, 3, 4 bonds? So the valency is 4, but only with 2 oxygens. And oxygen's got a valency of 2. So oxygen can only share 2 electrons. Yeah. So between this carbon and this oxygen, it shares 2 covalent bonds. And therefore we represent a C double bond O. We're going to do a lot of that when we start looking at, for instance, things like aldehydes and ketones and carboxylic acids.
How do we add the electrons on the lines to show which one is pulled more towards space?
The polarity of it? Yes, good.
So I don't know what it's called, but there is a way to show it where it's like, it looks like kind of like an hexagon.
Oh, that's when you're dealing with Kekuli structures, benzene rings. Yeah, but we don't do Kekuli. That's a little bit too advanced. But there is a way. Okay. Drum roll. Are you ready? Ready? Such an enthusiastic class. Hello. Huh? Thank you. Wait a minute. But this is the molecular formula. Okay? But there's another way of looking at this, and this is what I love about science. There are different ways of looking at the same thing. This can also be viewed as condensed structural formula, because what I'm doing is I'm explicitly showing what is connected to that carbon. Now, at this point, it looks like a molecular formula. But when I move on to ethane and propane and butane, you're going to see that looking at it from this perspective and looking at it from this perspective, you're going to get 2 different things. Okay. All right. Dennis, you look very sophisticated and intelligent with those glasses. Can you see what I'm teaching now? Very good. Okay. Now, all right. Okay. Let's move on. Okay. So we are going to look at something called the alkanes. Okay. The alkanes is a family. Please get this down. Alkanes is a family of organic compounds consisting of only carbon and hydrogen atoms and carbon-carbon bonds. Okay, carbon-carbon bonds and carbon-hydrogen bonds. Now, this is a bit of a long-winded definition. There is a more succinct, there's a more abbreviated version, but because I'm introducing it now, I'm really making it expansive. I'm making it like long-winded. Okay, so a hydrocarbon is a group of compounds that only consists of hydrogen and carbon. Okay, alcohols are organic, but they consist of carbon, hydrogen, and oxygen. They would be what we call carbohydrates. Okay, so we are going to first look at alkanes. There is a fancy name for an organic family called an ahomologous series. We will not talk about that today. We will talk about homologous series and functional groups and that sort of thing later on in this organic naming and structures series of lessons. Okay, now, all right, so with the alkanes, they only consist of carbons and hydrogens, and between the carbons, there's only single bonds. All right, a family of organic compounds consisting of only carbon and hydrogen atoms and carbon-carbon and carbon-hydrogen bonds. So what I want to start off with now is with how we name. So we're going to look at the prefixes. We're going to look at the prefixes, and the prefixes are meth, and you need to write this down. That means the carbon, the organic compound's got one carbon only. Eth, 2 carbons. Meth, eth, prop, 3 carbon. So when you say one carbon, one carbon atom, 2 carbon atoms, 3 carbon atoms. Meth, eth, prop. Bute is 4. 4 carbons. Bute, not but, bute. Okay. Pent is 5 carbons. Okay. Hex is 6 carbons. Hept is 7 carbons. Oct is 8 carbons. Non is 9 carbons. And dec is 10 carbons. Now, the official syllabus only expects us to teach you up to 8. Only expects us to teach you up to 8. Meth, eth, prop, bute, pent, hex, hept, oct, non, dec. Meth, eth, prop, bute, pent, hex, hept, oct, non, dec. You do it by means of rhythm. Okay. The way I learn is I like to move, and I like to say, and I like to get the association through movement. Notice what I say: meth, eth, prop, bute, pent, hex, hept, oct, non, dec. There's all sorts of acronyms. Some of them can be interesting. Okay. Now, when it comes to alkanes, the suffix is going to be ane. Okay. So we've got the prefixes. Now, these prefixes, you do not get given them in tests and exams. You need to learn them. And they work for all the compounds we are working with. All the compounds. Okay. So those are the prefixes. Now, with the alkanes, ane is the suffix. This is the suffix. So the suffix is what occurs at the end. So let's look at the naming. So if we talk about methane, then this means there's only one carbon, okay, and there are no double or triple bonds. There are carbon-hydrogen, there's no carbon-carbon because there is only one carbon atom. All right? Try ethane or ethane. So give ethane a try. Ethane. Thank you. ethane. How many carbons? 2, hey? So we're going to go carbon, carbon. Now, something that is very, very, very important about organic chemistry is you must never forget the fact that carbon has a valency of 4. So this is my personal name for it. I call it the circular test, the circle test, the carbon circle test. So around each carbon, you always count 1, 2, 3, 4. 1, 2, 3, 4. When you are drawing or sketching these structural formulae, always use the circular test for carbon. 1, 2, 3, 4. 1, 2, 3, 4. Okay? So now that we've got that, that's fine. This is known as the carbon backbone. Here is the molecule. The carbon, like I've got a spinal column, I've got a backbone. These molecules have got a carbon backbone. All right? So this carbon backbone has got 2 carbons, and we fill the rest with H. Okay? Are we okay with that? Okay. Meth F, can you please do prop, but, pent, hex, hept, oct, non, dec? Can you do it now for me, please? You can draw them all in. It's such a good question, Josh. You would think they're all in a line, but because of sp3 hybridization, right, they actually land up not being in line. All right? Because of the sp3 hybridization, they land up being zigzagged. But we will represent them as all in a straight line. Okay, I will pass this around. Ladies and gentlemen, what time does this lesson end? Right now. Thank you very much. Please do that for homework. I will post it on Classroom. Thank you very much. I'll be with you now. Sorry, I'll be with you now.